All right, we are now recording, and let's get the slideshow set up from current slide. And I will, awkward way to do it, get my projector on. Okay. Now, let me turn off this light again. Whose stuff is this? Is that ours? Huh? All right, before we get started picking up where we left off last time, and the sad news is I'm only talking to now 3 students, okay, that you're here. Increased the class size significantly. And this is Coco? Mm-hmm. Okay. All right. Let me just briefly talk about, I guess, things I need to talk about. Let's start with this. Papers. This class is probably ahead of most, if not all of my other classes. 1, 2, 3, 4, 5 papers have been turned in out of 15 students. That's a third, but we're more than halfway through the mini-term, okay? So that means we're not where we need to be, but y'all are at least making good progress. If you haven't worked on your paper, please work on the paper, okay? Now let's go over quickly these. Labs. About 2 people who haven't turned in lab 1. 1 person that hasn't done test 1. If that 1 person to complete test 1, I can return all your test 1s to you. Lab 2, 1, 2 people haven't turned in lab 2. Test 2, 2 people haven't done test 2. Lab 3, that's the moon lab. Hopefully you're making progress on that because you're running out of moonlight. The moon's not going to be up that much longer, so I hope you're making progress there. Test 3, let me see here. I think everybody has now completed test 3, so I can return test 3 to you. And this is sort of sad. Finally a day I can return something to you, and I have 3 people here. So, sorry about that, but I'm glad to get rid of any that I can. Test 3. I should have done this while I was. So awkward to have to work from here. All right, here is test 3. Let me make sure I didn't realize. Yep, I guess last time someone completed the test. I'm going to put Brendan's here on his books. Brianna's not here yet. Gary's not here yet. Emmanuel is. Tara, I'll put hers on top of her books here. I hope she'll be showing up. So that was Tara. And Coco. Bianca's not here yet. Dave's not here yet. Josh is. Good. And the rest are not here yet. Carrie, Carl, Tanisha, Shelby, Brittany, and Terry. All right. So if you're listening to this and weren't here, you can't get your test 3 back. Lab 4. 1, 2, 3, 4, 5 people haven't turned in lab 4. Oh no, I'm sorry. Lab 4 was the trip to the planetarium. If you were there, you got your 25 points. If you weren't, you did. Lab 5. 1, 2, 2 people haven't done lab 5. Test 4. 1, 2, 3, 4 people haven't done test 4. And then we'll pick up from there. So probably took too long, but there's that. Now, today, we're going to spend about the first 2 hours. I'll return your 3rd test to you. Have you got anyone coming?
I wasn't around there, so I didn't know what to do.
Oh, okay. You want to see if my work study student can come take notes for you? What's that? Okay, let me see. Did you hear your name called in the bus? You gotta go. Okay. Brandon does that, and I'll take notes for him. If you don't mind. Yeah, that was the only issue here. I've managed to learn to read his writing, but sorry. No, you all don't say that. Okay, but do you have someplace you want him to take them, or does he bring something and just get to you?
Usually put him in this notebook.
And you got a notebook. Okay, he's got a notebook already, Cameron. Okay. All right. So today we're going to continue chapter 19 and go until about 2:30. Okay. I think we'll finish 19 before 2:30 gets here. If we do, that'll be fine. If we do finish it before 2:30, we'll go on and start chapter 20. Okay? But at 2:30, we'll pause wherever we are in 19 or 20, and then we'll move on to the lab. And it's basically the chapter 18 lab, but it really doesn't have that much to do with chapter 18. It's just another lab from physical science. Okay? So there's that. Then at 4:30, or if you finish the lab earlier, we'll stop earlier. And then at 4:30 or whenever the lab's through, then we'll have the test on chapter 18. So it's the chapter 18 lab, which really doesn't have that much to do with 18, but some. Sort of a fun lab. I think you'll enjoy it. And I think it'll go fairly quickly. Hopefully it will. And you can work together. But it's going to be a cluster buckshot here for a while. And then the test on chapter 18 will be the last 30 minutes. Don't think it'll take you 30 minutes, but we'll have that. And then we'll plan for next time. Have class, we'll pick up either at 19 or 20, wherever we leave off today. And again, have, if we finish 19 today, we'll have 2 hours of class, 2 hours of lab, and then 30 minutes on the chapter 19 test. Okay. Okay. So, any questions? I think I said that right. I may have said, no, actually, the chapter 19 test, I found the test bank so unsatisfactory that...
Your work studies do make one?
Huh?
You said that you're going to have to make your work study make one?
No, that I am giving you a take-home test. It's all fill in the blank because I thought their multiple choice questions were just too obscure, opaque. I couldn't get enough of them to make a good test. So it's going to be a take-home test. So when we finish 19, if we finish it today, while y'all are taking your chapter 18 test, I'll go run off the chapter 19 test. Because I have it ready, but it's not, I don't have copies made yet. All right. Any questions how we're going to proceed then? Okay. So where we're going now is, this is where we left off last time. We were talking about earthquakes, hopefully not experiencing any. And on earthquakes, we talked about the causes of earthquakes. We talked about locating and measuring earthquakes. And the last part of that is how we classify these earthquakes, which is based on some sort of a measurement. The major classification, remember earthquakes are wherever you have hang-ups, okay, in the motion of plates with each other, or portions of plates. Some other type thing that's creating these perturbations in the Earth's surface. Okay? Shelby's here. And I did return to the folks who were here, the test 3. So if when we start doing lab and that kind of stuff, if you'll remind me, I'll get you your test 3. I don't want to dig through the pile and get it now. Okay. So what happens with earthquakes is when there's a shifting of something, usually plates, but not always plates. But when they shift or things happen and there's sudden release, the rebound theory, either elastic rebound or brittle fracture rebound, whenever that happens, whichever is happening, Bianca's here. Okay. And for those who just came in, I did return your test 3s to you today. So during lab or test today, I can return yours to you. I just don't want to dig through the pile again. Okay. And just another reminder, we're continuing chapter 19 now. We'll do that for approximately until about 3:30. Okay. At 3:30, we'll stop and have the lab that kind of goes with the last chapter, 18. It's the lab that accompanies that chapter, even though it has very minimal to do with it. But it's just a compiling of everything we've done so far. And when we finish with that, or 4:30, whichever comes first, you'll have the test on chapter 18. Okay? All right. I've already returned your paper to you, but you didn't get to hear this. I returned test 3. Okay?
What day was that?
What?
Test.
The test on chapter 18 is Tuesday. Next time we meet. The last 30 minutes. Okay. No, wait. I'm sorry. Chapter 18 test is the last 30 minutes today. Okay, the chapter 19 test, the one we're on now, is a take-home test, which if we finish the chapter today, I'll go down and or maybe find the work study student to send down. No, I'm just kidding. to make copies. I think he'll be gone by then.
We're doing the test.
What's that?
The test today we're taking home.
No. The chapter 18 test is in class. That's at 4:30. The test at the end of chapter 19, though, whenever we finish that, today or Tuesday, that will be a take-home. I'll just give it to you to go.
What are we taking it home for?
You can do it here if you want to, but yeah.
Oh, it's using the same time.
It's open book. Well, the thing is, most of the other tests have been multiple choice. The test bank for this chapter, I found their multiple choice questions either unreasonable, unclear,
Like one,
esoteric. Say
like
again.
one answer might have like two like sort of similar like synonyms or things like that.
Something like that, or else they just, I didn't think they were really testing the material well. The only way I could think of doing it is to take them and change them into fill in the blanks. And fill in the blanks, just a couple questions each test, I can usually figure out your spellings and stuff like that. But when the whole test is on that, I thought, let you take it home and spell it right. Okay, so that's why I do that one. And then too, in case some people are struggling with the test, which most of you are doing quite well on your test, but it gives you a chance to have a pretty good score if you put the effort into it. Of course, if you don't put any effort into it, you still have a mediocre score. I've had them before, but most of the time, this is a pretty good score. All right, now, so we were talking about earthquakes, why they happen, because there's sudden release of energy. Pressure builds up, usually between plates, or for some other reasons within plates. There's pressure, tension, something, and then something gives, and we have those. So the classification is based on where that occurs. Remember, what do we call the point where the earthquake actually occurs? What's the name of that position? Okay, the epicenter is the surface of the earth above which the actual quake occurred. What is the place where it actually occurs? The focus. The focus is actually where the release of energy happens, and then the waves move out from there. The epicenter is the place on the surface directly above the focus. So, the classification of earthquake is based on the depth of that focus. How far down is it that you have that? The shallow focus earthquakes are down to about 70 kilometers deep. Whoa, okay? That's about 42 miles deep. They call that a shallow earthquake, okay? 42 miles into the earth. But it is shallow. You're barely probably out of the crust, just in the early part of mantle, probably there. That may vary wherever you are. But 85% of all earthquakes happen in that first 70 kilometers. Now they give a reason here, okay? Remember, it's where the plates or other things have gotten hung up and then suddenly give, either by elastic rebound or fracture rebound. That happens most likely near the surface, because near the surface the rocks are rocks. They're solid. They're cool enough to be brittle. As you go deeper and deeper, you run into hotter and hotter. The hotter things get, the more plastic they become. And then the likelihood of an earthquake, it still happens, and it can happen, but the likelihood is less so. More happen on the surface. There's more plate friction near the surface. When you get hotter and it gets more plastic, there's less friction. Hot, but it doesn't hang up as badly. So those are your shallow focus earthquakes. The intermediate focus earthquakes are between 70 kilometers and 300. Now here they have an error on the slide. It's correct in your book. And yeah, that's 350. Okay? You notice what happens to those earthquakes between 300 and 350 kilometers? Well, they don't know. They don't exist. That's a make-believe earthquake. Fake earthquake. Okay? Let me get... Okay. You called it. Okay. That's 350 there. Okay. Now, what is 70? We said it was about 42 miles. 350 kilometers is about 220 miles, and they call that intermediate. Okay, 220, or whatever I just said, miles down, that's a long way. 42 miles is pretty far for me. 200 and some odd, that's even further. I mean, that's a long way down. Intermediate, you're definitely in the mantle, the upper part of the mantle. Here we're still mostly the crust, maybe getting a little bit into the upper part of the mantle, but this is the upper part of the mantle. Now, they didn't give a percentage there. Let's go on to the deep focus earthquakes. Deep focus earthquake between 220 miles to 430 miles deep. Did y'all realize the mantle was that thick? You're still in the mantle here, and it's the, but you're way deep in it. I'm sorry. You're still in the upper mantle. Remember, the upper mantle sits on the what? One of the spheres. Asthenosphere, exactly. Asthenosphere, remember, is the elastic plastic, the semi-plastic, semi-liquid, semi-solid layer there that the plates float on. Okay? So all your earthquakes are where the plates are. You can't be in the lower mantle. You have to be above the asthenosphere. Now, what do we call that? Another sphere between that asthenosphere that includes the upper mantle and the crust. The lithosphere, exactly. All your earthquakes occur there. This is in the lower part of the lithosphere, which is the lower part of the upper mantle. Okay? And these are, as I said, from 220 to 400 and some odd miles deep. Whoa. Then you hit the asthenosphere, and you still have a lot of mantle to go, but we don't go down there. Okay? We don't go even that far. Only about 3% of all earthquakes are those deep focus earthquakes, which leaves how many in the intermediate focus? What percentage?
Right.
About 12%. About 12%, because you have 85% in the crust, okay, maybe just beginning to be the upper part of the mantle, but most of the upper part of the mantle is 12%, and then only 3% down in the lower part of the upper mantle. Okay. All right. So that's our classification of earthquakes. All right, we've covered on the next page most of those figures there. The next topic here is how do we measure earthquake strength? Now, this has gone through a series of measurement schemes, okay? How do we go about measuring? Do we measure the effects that we see on the surface? That's the most obvious thing. Or, and I think I gave you the example last time, didn't I? Within just a couple of months of each other, about, I think, 6-8 years ago, y'all remember when Haiti had the big earthquake?
Yeah.
Okay? But guess what? It wasn't that big of an earthquake. It did an incredible amount of damage, but because the earthquake was that strong, it was strong. I mean, it was strong, but guess what? It was because of poor building code in Haiti. Most of the structures were concrete blocks, which have they don't do a good job standing up to earthquakes, okay? And wood structures, without any reinforcement. Enormous amounts of damage, okay? So if we'd gone the effects of the earthquake, that was one of the most devastating earthquakes we've had anywhere. But it wasn't one of the strongest earthquakes. So do you go by effects or do you go by something else? Well, the effects: structural damage to buildings, fires, landslides, displacement of land surfaces, tsunami or tidal waves. There's lots of ways we can measure that, especially if we're looking at the effects of it. All those are things that happen because of the earthquake. Structural damage to buildings, fires, landslides, displacement of land surfaces, and tsunamis are all caused by earthquakes. But that's probably not the most scientific way of measuring an earthquake. That also is measuring the societal issues. So what if the earthquake happened somewhere that no one lived? There wouldn't be much damage to structure. But if it was a really powerful earthquake, it's still a powerful earthquake. So that's probably not the best way. Later they came up with a scale. A guy, I think he must have been Italian. It sounds like an Italian name, Mercalli. The Mercalli scale was relative intensity. And again, this is something that's a little bit subjective, okay? Not completely objective. In other words, number 1 on the Mercalli scale was you don't feel it, but you know it happened. Number 12 on the Mercalli scale, total destruction with visible ground waves. And James is here. Okay, somewhere. Oh, you're in. All right. Now, again, let me say this for James's benefit, just so you'll understand what's going on. First, I did return test 3 to people because the last person who hadn't done it did it since we last met. So during lab or test, if you'll come up and get your test 3, be glad to get it off my pile. Other labs and tests, I'm still waiting for at least one person to do. So if you haven't done a test or a lab, please get those in. Do this every term. Why people delay so much? Anyway, I'm probably preaching to the choir because y'all are the ones who got most of it in. Okay, so Mercalli scale, again, pretty relative, pretty subjective. You feel it, or total destruction with visible ground waves. Well, that could be a measure of how poor your buildings were. I was going to say before, when I mentioned the Haitian earthquake, it was within, I think, just a few months after Haiti had the big earthquake. Chile had one. But Chile's was far more powerful with way less damage. The reason? Chile was right there on the Ring of Fire. They have had a history of earthquakes, so their building codes were very strict, a lot like the ones in California, especially around San Francisco, Los Angeles. Their buildings have to be able to withstand. So the damage was, I don't want to say minimal, but far less than the one in Haiti. Yet, it was a far stronger earthquake. So, again, this could be pretty subjective. Okay? Let's see if they have the breakdown here. Oh. You'll see this again, I think on a better slide, so I'm not going to go into it right now. If my memory's wrong and you don't see it again, I'll come back to this one. So this is just what to do or not do if you happen to be there when an earthquake occurs, okay? Now, the Mercalli scale, I think the old text used to go into it. The verbiage in your book goes into a lot more, okay? This just gives the number 1 and number 12. In your book, you'll find a lot more detail, okay? And, you know, I'll let you read that, okay? Because we don't use it anymore, but just to let you know. Before we move on, there is another mistake and misunderstanding, fairly similar to the one we had last time, was, is California going to fall off into the ocean? No, it isn't. That's not what earthquakes do. In science fiction, or in just fiction, on the movies, maybe that happens. The earth opens up and people fall in. That doesn't happen in real life. That's fabrication, okay? This one, though, is, do earthquakes swallow people? Same type deal. No. They shake the earth. That's all they do. They don't open up and people fall in. So, now we get to measuring earthquake strength. A guy named, I think it was Charles Richter, and if I'm not mistaken, he was from California, an American seismologist at California Institute of Technology, the early 1930s, Caltech, one of the premier technological institutions probably in the world, but certainly in the U.S., okay? And Charles Richter came up with a scale that's not based on the damage done, the subjective measure like that. It's based on, they have the seismographs, use the seismographs, the swings in the seismograph recordings. How strong was the earthquake? This way, if it's on some island down in the South Pacific where no one lives anywhere around, so there's not much damage done, if it was a strong earthquake, it records it as a strong earthquake, okay? But it's based on those swings of the seismograph. They use a log scale. Now, does anyone know what I mean by logarithmic scale? Okay. Basically, what a log scale does for you, it makes big numbers into manageable numbers. It's a scale that does that, okay? And it does it by dealing with the powers of the numbers, not the numbers themselves, okay? And especially when you have a huge range of numbers, some of them getting very, very big, and if you tried to plot that on a graph, your graph would be enormous. What they do with the log scale, it literally scales things down pretty well. Now, number 3 on the Richter scale is like 1 on a Mercalli scale. You don't even feel it. But the seismographs can read it. They can read even things less than that, a 2 or a 1, okay? They register those, but you're never going to feel those, okay? And it goes up to 9, which is the largest measured so far. And if I'm not mistaken, this was in Alaska, though I think they've had some other pretty powerful ones, but I think the most powerful was in Alaska. And by the way, where does Alaska sit? on the ring of fire, okay, where the plates collide. And sure enough, somewhere inland in Alaska, there was a major, major quake. Now, on the one hand, it was a pretty remote area, so there wasn't a lot of structural damage. So back on the Macaulay scale, or the original way of doing, no biggie. But it was a powerful earthquake. It was so powerful that the tsunami, which is what? Another name for a tsunami? A tidal wave. The tidal wave that came from this quake, it was so powerful, it flooded parts of Hawaii. A long, long, long way away. I mean, it was major. Okay? So actually probably more structural damage happened in Hawaii than happened in Alaska, though I don't know that for sure. Okay. And then you got everything in between. Now here's a key to a log scale. What if we had named something in between those numbers? Earthquake of some magnitude. Pick a magnitude.
7.
7. Magnitude 7 earthquake. Okay, now pick another one, either bigger or smaller than that. I don't care.
4.
A what? 4. Okay. So a magnitude 7 quake, a magnitude 4 quake. How would you compare those? Certainly the 4 is less than a 7, but how much less? Half? A little bit better than half?
I'd say a little bit more than half.
A little bit more than half. That's what it sounds like, doesn't it? What that means, the 7 quake is 3 more than 4, right? 10 to the 3rd power. 1,000 times more powerful than the 4. Every number in the Richter scale, the log scale, means you go up by a factor of 10. So 4 to 5 was one factor of 10, 5 to 6 was another, and 6 to 7 was another. It was 1,000 times more powerful. Not twice, not a little bit more than twice, 1,000 times, because that's what a log scale measures. It takes big numbers and scales them down to manageable numbers. Now, Richter scale is the only thing that uses this. Other scales do too. Have you ever heard of the term decibel level? What does that measure? Yeah, sound. You know, it's the loudness of sound. Now we have incredible bodies, really. You know, I mean, most of you do. I don't. You know, most of you have pretty great. What's incredible about them is the range at which things do. We can see a little spark a long way away, or we can see really big, bright things fairly close, okay? You'd have to have, and we don't have a scale for it, or I don't know of one, you would have to have a log scale to measure that range. Same thing with hearing. Okay, you probably may or may not have heard that, but the softest whisper you can have, compare that to a jet plane taking off, or a rock concert when you're right in front of the speakers, the range between that is enormous, and yet our ears can detect all that. So, what they do, a decibel, the deci means power of 10. So that is a log scale. The decibel level, the difference between a 4 and a 5 is 10 times. Okay? 10 times as much. Okay? So, same thing here. pH scale. You know what that is? That's exactly it. Concentration of the hydrogen ions. You're absolutely right. Now, it's a negative log scale. So the higher the concentration of hydrogen ions is the lower the number on a pH scale. And the lower the number of hydrogen ions is the larger number on the pH scale. Strange, but that's what they do. But what you're measuring there, anyone know what absolutely neutral is on pH? 7. No, 7. That's where you start, 7. And where do you get that? it's the concentration of pure water. Water is hydrogen hydroxide, by the way, H2O, one hydrogen ion, one hydroxyl ion. Hydrogen ions are your acidic ions, hydroxyl are your basic ions, okay? So the more hydrogen you have, the fewer hydroxyls, the more hydrogen, okay? Pure, whatever, okay. Now, pure water, absolutely pure water, breaks down to 10 to the minus 7 is the concentration of hydrogen ions. It's exactly the concentration of hydroxyl ions, too. Absolutely pure water. I talk about water and Brendan gets thirsty, right? Okay. So the pure water is 7. Now, if anything's more acidic, the hydrogen ion concentration goes up, which means it's a smaller number. Absolute value, because 10 to the minus 7, if you got more, that would be 10 to the minus 6 or 10 to the minus 5. So what you do then, if you take the negative of that log, that would then be dropping, okay? Because you take the negative of the log. What is it you drop? The lid?
Yeah.
Oh, okay.
Yeah, thanks a lot, Mr. Long.
Okay. All right. So that's a log scale too, because the concentration of hydrogen ions vary hugely. But your pH scales run from, I guess the most acidic things you have is maybe a 1 or a 2, but most of the things you would encounter would be up, maybe 4 would be very acidic. But then your most basic things would go up 8 or 9, maybe 10. Okay, so again, those are log scales. Okay. Richter scale is measured in log scale. So here are the effects of earthquakes of various magnitudes. The Richter scale is an objective scale measured from the swings on seismographs. How much energy is being released, okay? The 0 to 2s on the Richter scale are your smallest detectable earthquakes. They can detect them with the seismographs, but you're not going to feel anything, okay? 2 to 3 are detected and measured, but generally not felt, okay? Again, you can detect them, you can measure them, but usually you're not going to feel them too much, okay? 3 to 4, they're felt as very small earthquakes with no major damage, okay? I think I mentioned to you the one that they occurred somewhere, I think in Virginia. I know it influenced Washington, D.C. pretty strongly, but down in Georgia, I was telling you about that, we had things fall off the wall there. So it did have a range, but that's probably 3 to 4, maybe 4 to 5, because there was enough damage to the Washington Monument they had to close it. But I didn't hear of many other things that really were damaged that badly. Okay, this isn't a high-risk earthquake zone, by the way. 5 to 6 or 4 to 5 is minor earthquake with local damage. That could have been that one that we're talking about, 4 to 5. 5 to 6, moderate earthquakes with structural damage. I guess maybe that one, since the Washington Monument did have structural damage, but it wasn't a lot. It could have been in the 5 to 6 range. But 6 to 7, strong earthquakes with destruction. Okay? 7 to 8, major earthquakes with extensive damage and destruction. And that would have been the one in Haiti, I'm guessing was a 6 to 7. I don't have that number in my head, but I think it was somewhere in the 6s. The 7 to 8 probably was the one in Chile, okay? So, and my guess is the one off Fukushima that caused all the damage to the nuclear power plants there. That was probably in the 7s as well. Let's see if I can remember. A few years prior to that one, I'm pretty sure it was, there was another one really close to Christmas then too, that was in Indonesia, or off Indonesia, Thailand, somewhere in the Indian Ocean there. Do y'all remember that one? Major tidal wave went as far as India which is a pretty good distance away. And yep, here we are. I don't know if you can see it from where you're sitting, but here is Indonesia, and Thailand and those areas are around here. The tidal wave made its way all across the Indian Ocean and did some pretty major damage in Madras, which I think at that time, yeah, it was called Madras then. It's now being called Chennai. We actually have friends from that area. Tamil Nadu is the province, and they had family members out enjoying a warm day at the beach. And I don't know if their tsunami warnings didn't happen or they didn't hear it, but people got, because that tidal wave came in, it's still several meters high. So whereas normally the waves just run around your feet, these would have been like story buildings coming in, and quite a few people did get drowned. Fortunately, our friends, all of their families were accounted for. Someone somehow detected something. It may have been the animals alerted to it. They saw something coming, and everybody who was aware enough, they just started heading inland, higher elevations. And many things got destroyed pretty badly then. So that was probably a 7 to 8 then too. The great earthquakes with total destruction, those are your 8s and 9s. The largest so far measured being a 9, around 9. But there have been some pretty major earthquakes. I mean, there's not much you can do. There's no building codes that's going to protect you from those, okay? But a good building code can do at least save people from a little bit lower. The one in San Francisco around the turn of the beginning of the 20th century, enormous amounts of damage, but more damage was caused by fire than was caused by the earthquake, because they had gas lines, wooden houses, and just it was a major, major fire there. Since then, the one in the Bay Bridge area during the World Series, that was quite a few years ago, that was caused considerable amount of damage, but they had better building codes, so it was a far stronger quake and did much less damage than the one a century earlier, okay, close to a century earlier. And then the one in Los Angeles, I don't know if they hadn't enforced the codes there, but Los Angeles wasn't used to getting them like San Francisco was. That had some pretty major damage too. I'm guessing that was probably down in these ranges, 5 to 6 or 6 to 7. Okay, still lots of damage there. That's how we measure earthquake strength. This is the slide that was up there before, and I said you'd see a better copy of it. So here it is, so you don't have to read the very fine print. Earthquake safety. What should you do if you were to be in a place where they were experiencing an earthquake? Well, guess what? If you're feeling the earthquake, there's nothing you can do then. So don't panic, okay? Keep your head about you, okay? If you're already indoors, stay there, okay? If the building hasn't fallen on you already, it probably is not going to, okay? But stay away from glass. This room would be a great room to be in if there was an earthquake, as long as the ceiling didn't come down on us, okay? Probability of this wall coming down, pretty slim, because we've got soil right against us, but I guess it could happen. You wouldn't want to be on that side of the hall where you have lots of glass, because more than likely the glass will do some major shattering, okay? Now, do not use any other flames. Lights go out, don't pull out your cigarette lighter. Okay, why? Like I said, in the San Francisco quake, the early one, the fire killed more people than the quake did. The reason? Gas lines broke. And I know there are gas lines in this building because chemistry labs use them. I don't think our heating system uses them, but there's a low probability, but we could have some gas leakage here. Don't pull out a cigarette lighter. Hey, we got to see how to get it. Well, you have cell phones, you have your flashlights on that anyway. Okay. Don't use any other, I think this means open flames. Don't use any other flames. What other flames? Okay. If you're outside, then get away from the buildings, because if anything's going to happen, the buildings are going to fall down. So don't feel like you'll be safe to get near a wall. No, the odds are if you're outside, you're okay. Okay. Stay out in the open somewhere. If you're in a car, stop as soon as you can, but stay in the car. The car gives you some structural strength around you, but don't be traveling. Unless you happen to be under a bridge or an overpass, get out from under that. Don't think, oh, I'll get under here, it'll be safe. No, that's one of the worst places to be, because as evidenced in the San Francisco quake and the Los Angeles quakes, those things can fall down. Pretty major, okay? Now, after the shaking, it says check, but do not try to turn on utilities. Okay, maybe the power went off, so don't go to the switchboard and just start seeing if you can find which breaker did so you can turn it back on. You may have a major short in the system, and that's why the breaker did. You start fiddling with that, you could either start a fire, shock yourself, shock somebody else, so don't try to turn on utilities. Check them. When they say checking them, I think they're talking about gas mostly. If you hear, you know, like there could be a gas leak, get away or see if you can find the valve to turn it off, not to turn it on. If you smell it, most of the natural gas has been added an odorant to it, so you can tell when the gas leaks. If you smell it, alert somebody. If you don't know where the valve is, get out of there. Okay, get out of the range where you smell that going on. Check, but do not turn on the utilities. If you still have power or a battery-operated radio, then turn on the radio and TV and see what they're saying. Okay? Now, this will be the hardest for most people to do. Stay off the telephone unless you're trying to report an emergency. Like a gas leak. Gas leak, you smell or hear the hissing of the gas, get on the phone, tell somebody, get out of there. Give them the best location you have, get out of there. That's about the only time you get on the telephone, because the lines need to stay open for emergency responders. Not, hey, did you feel that? You know, how's it at home? You know, get off. Don't even get on. Okay? Now, this is after the shaking is over. Stay out of the damage. Hey, but my wallet's in there. Who cares about your wallet? The building could have aftershocks. The earthquake could have aftershocks. And that damaged building may become a rubble pile and you could be in it. So stay out of damaged buildings. And by all means, and this happened back, remember the Oak, or what's the community that had the tornado several years ago? Second? No, before that one. Community a little bit northwest of here. Second? They may have had, no, that was all that same earthquake with Tuscaloosa. There was, I want to say Oak Ridge, that's not the name of it. There was a high school there that was totally destroyed. I can't think of the name of the place. Seemed like Oak was in the name of it. Yeah, they had a major one, and people started, hey, I heard they had an earthquake, and they went driving, and people couldn't get through. Emergency vehicles couldn't get through to get to people who were in dire need of emergency services because the roads were blocked. Okay, it happened with the Tuscaloosa quakes. Tornadoes, but it was all over the state, so you just needed to stay off the road. Now, another thing, let's go back to here. Stay in the car. What's another reason to stay in the car? Besides the fact it gives you a little more structural support, if you're on the road, a lot of roads have power lines going near them. If you get pull over, not a good idea to get out and start walking around and happen to step on a power line. If it's or touch, and this has happened too, a power line actually comes up and is touching your car with a good bit of power, but it has no way to get to ground until you provide the path to get to ground, then you're electrocuted on the spot. So that's why it says stay in the car also. And by all means, don't go sightseeing. Leave the roads and the places open for emergency vehicles to get through. It's a lot the same as you see for tornadic or other disasters you may have. All right, any questions? Earthquake safety. This, by the way, is top of page 490 in my text. Okay. Now, we haven't been doing many of these, and I wonder if this one's worth doing or not. Let me refer you back. I gave sort of a quick rule of thumb, and it's fairly close, but not exactly accurate. Here's the better rule of thumb. It's on page 489, or whatever the page is. If you find the Richter scale, table 19.1, talked about Charles Richter, that kind of thing. In that very paragraph, the higher the magnitude of an earthquake is measured on the Richter scale, the greater two things: severity of ground-shaking vibrations, that's really what it's measuring, but number two is the energy released by the earthquake. Okay? Well, this is what we were talking about before. An increase of 1 on the Richter scale means that the amount of movement of the ground increased by a factor of 10. 6 to 7, 4 to 5, that's a factor of 10 of the movement on the ground. But the amount of energy, that increased by a factor of 30. Not 10, but 30. So the energy release was a factor of 30 for every 1 unit that goes up. And that's because energy and displacement is not a one-to-one relationship. Okay? And as it says here, the largest earthquake measured so far had a magnitude more than 9, but there is actually no upper limit to the scale. I mean, they could get even bigger. Okay. So with that in mind, let's look at example 19.3. In my book, it's on page 490. Compare the energy released by an earthquake of magnitude of 7.2 magnitude on the Richter scale. And let's go back to that. 7.2 would be a major earthquake with extensive damage and destruction. Okay? To an earthquake of magnitude 5.2. That's moderate earthquake with structural damage. Okay? The question is, compare the energy released between those two, a 7.2 and a 5.2. Any of you do that? Energy released is how much for every single point?
It would be 100 times.
Okay, no, okay, that was the movement. The movement would be 100 times stronger, more movement. The energy is 30 times for every point. So it's 30 times 30 is 900 times the amount of energy released. Okay? Because you got a total of 2 points between the two. Every single point is 30, and 30 times 30 is 90. Sort of like we did before on movement, 10 times 10 times 10. So that's where you got your 100, 10 times 10. That's movement, but that's not energy. Energy is 30 times 30. And then it said, example 19.4, Brendan was just looking ahead, compare the amount of movement of the ground, surface wave amplitude associated with the two earthquakes, and that would be your 100 times between 2 points. All right. Now, there's a little bit more there. There is a blurb on tsunami. I'll let you read that and take that in. There are is a table in the text here that is worth reading, I think. because it gives not only a measurement, but it also gives cause and some notes on it. And actually it's listing here. I was thinking the Alaskan quake was the most powerful. I thought I had read that somewhere, but it may not have been in this book. It may have been somewhere else. But in this table, they mention a 9.0 quake in Japan. Now, this was before, I think this was before the, goodness, I'm going blank. I've already said the name several times. Had the big tsunami and the nuclear damage, Fukushima. I think this was before Fukushima, but I think this book was published before then. But this was March 11th, 2011. Okay, 9.0 in Japan. A Pacific plate subducted underneath the, they've got this wrong, that's the Eurasian plate, not the North American plate. 6 miles or 9.7 kilometers. So what classification of earthquake would this be? 6 miles or 9.7 kilometers down. Okay, what was 85% of your quakes? Shallow focus. That goes down to 42 miles or 70 kilometers, way shallower than that. Okay? And it was 80 miles off the eastern shore. Now, catch this. A 9.0, 80 miles away, 129 kilometers away, 14,000 buildings destroyed. And if I know the Japanese, they have pretty good building codes. They experience earthquakes, so they had well-built buildings. 118,000 buildings damaged, more than 18,000 fatalities, that means deaths. Movement of the ocean floor created a 23-foot, which is 7 meters, tsunami. Okay? Now let's get a perspective on that. I'm about 2 meters tall. That means the ceiling is about 3 meters tall. So basically, 2-story building almost. 2-story building, wall of water coming in to a coastal area, that's going to do a lot of damage. Okay? And it did. Okay? I'm pretty sure this is not the same one as caused Fukushima, the nuclear reaction there. I don't know if any of you have a phone, you can look that up. It may have been that one, but it seems like it's awfully close to the same time frame. Now, before that, the 8.8 in Chile, that's the one I was talking about. The Nazca plate, and didn't you say you were down in South America? You were in Peru, not at this time, but that was the February 2010, late February, just about 7 years ago. The Nazca plate subducted under the South American plate. 370,000 homes damaged, and 486 fatalities. Wow. Compare that with Japan's, they had more than 18,000 fatalities. The movement of the ocean floor created tsunami up to 7.7 feet, which is 2.3 meters. So that would be about chest high. But a wall of water coming in chest high can do a lot of damage too. 7.1 quake in New Zealand, 9.4, same year, but a little bit later that year. A strike slip fault within Pacific plate. So this is all within one plate, but there was a fault within the plate, and that can happen at a depth of 6 miles. What kind of that be? 6 miles down, 9.7 kilometers? That's again the shallow focus. Anything down to 42 miles, which is about 70 kilometers, shallow focus. 85% of them are that. Okay? It's at a depth of 6 miles west of Christchurch, which is on one of the islands of New Zealand. Widespread damage, but no fatalities. No tsunami, since the epicenter was on land, not in the water. Okay? Okay. And by the way, New Zealand is an arc island made where either two plates or two faults within a plate happen to be rubbing against each other. Then the 7.0 in Haiti, that was 15 days before the one in Chile. I thought it was a month or two, but 2 weeks before. A fault system between the Caribbean and North American plates slipped. Okay? Now 7.0 is a pretty major quake. 7.0, that's a major earthquake with extensive damage and destruction. So yeah, it was big. Okay? Earthquake focus was 6.2 miles or 10 kilometers below the surface. What kind of quake? What classification of quake? Shallow focus again. All these are shallow pretty much, right? 85% of them are. Now get this, okay? Haiti, 7.0. Chile, 8.8. That's almost, I'd say about 80 to 90 times more movement and 700 to 800 times more energy released in Chile. In Chile, 486 fatality. Oh, wait. 370,000 homes just damaged. In Haiti, 97,300 houses destroyed, totally destroyed. In Chile, 486 fatalities. In Haiti, with a much weaker quake, but still very strong, 222,600 fatalities. Now, there's other things that enter that picture too. Chile is a pretty sparsely populated country. The big cities, yeah, they have large population densities. I don't know exactly where this quake was, but it probably was not right under that. Unfortunately, the Haitian quake was really close, and Haiti is a very densely populated island, extraordinarily densely populated. So no wonder there's a lot more fatalities. But that number more for that weaker quake. Then again, 6.3 New Zealand. This was in 2011. A strike slip fault again within the Pacific Plate at a depth of 3 miles. That's 4.8 kilometers. What's that? Shallow again, really shallow. And this is 25 miles or 40.2 kilometers west of Christchurch. And the other one was also west of Christchurch. Widespread damage and 182 fatalities. Okay? So 1 year later, a weaker quake, okay? In fact, not even a year, more like 5 months or so later. 7.1, widespread damage but no fatalities, no tsunami. The damage was on land. And this was west of Christchurch. But then the one 6.3, 9 months later, widespread damage, just like before, 182 fatalities, no tsunami since it was on land. It's a different fault than the earthquake that occurred 6 months earlier. Okay? So why were there so many more fatalities? Beats me. Okay? Unless maybe the first quake had damaged buildings and they hadn't had time to repair them. It was only 6 months later. So the weaker quake came later from a different location but it had more fatalities. Okay. Maybe that's enough about earthquakes. Let's move to mountains. This is section 19.4. What are the origin of mountains? What is a mountain anyway? An elevated part of the Earth's crust rising abruptly above the surrounding surface. So when you leave, say, Tidewater, Virginia, and you start getting away from the coast, sure, you're going up in elevation. That's not a mountain. Now, even if you continued up in elevation, as long as it was gradual increase, which you won't find in Tidewater, Virginia, but if you did, you're still not on a mountain, okay? What they mean here, the elevated parts of the Earth's crust that rise abruptly above the surrounding surface. What's the tallest mountain in the world? Everest, okay? Is that the tallest above the surrounding surfaces? No, because Everest is on top of the Himalayas, it's up in the Himalayas. Everything's high up there. Actually, Kilimanjaro in Africa is the tallest from ground level to the top. Not nearly as tall as Everest, but Everest is way up to begin with, and then it's tall. Okay? Whereas Kilimanjaro is on a fairly low level, but it just rises incredibly above the surface. Okay? But both of them are mountains because they're both rising abruptly above the surrounding surface. Now, we're going to talk about two types of mountains here, and then later we're going to talk about a third type. So in this bullet here, they're only talking about folding or faulting. And here's sort of a quick, and you can't say this is always true, but the Appalachian Mountains are pretty much folded mountains, okay? They're not really near a plate boundary, because the North American plate goes out about midway to the Atlantic Ocean. So you're not near a plate boundary. However, there are weaknesses in the plate there, and the rocks folded. Okay? The Appalachians are predominantly folded mountains. You go out west, however, and the Rockies and the Sierra Nevadas are fault mountains because they have actually slipped. The hanging wall, footwalls, they've actually had faults, and they're much more jagged. If you look at the Appalachians, they're mostly rounded top. Okay? They're rocky top. No, that's not correct. But they're rounded top mountains because they're folded. The Rockies are very jagged and pointed because there are fault breaks there. So that's a generalization. I'm not saying there's no fault mountains in the Appalachians. There are. I'm not saying there's no folded mountains in the Rockies. There may be some. Okay. So, three basic origins: folding or faulting of the plates, or volcanic activity, where magma comes from below. When it reaches the surface, it's called lava, and then spews and makes new material. Those are volcanic mountains. So we'll look at all three of those. Well, actually, we'll look at folded and faulted together. Your domed mountains begin as a broad arching fold, so that's a folded mountain, okay? The arches, what would you call another name for the arch? Oh, how long ago it was. Starts with the same letter. Arch. Anticline. Remember that? Anticline. Okay? And the trough was syncline. Exactly. Okay. Now these dome mountains generally are overlying sedimentary rocks. They weather away, and then they leave the more resistant granite peaks. Okay? The folding occurs beneath. The sedimentary rocks that are on top of the granitic rocks, okay, and there's several things that are going on here. We'll talk about this more in the next chapter. But as the folding occurs, your surface gets stretched. Just imagine a mole going under the ground, okay, making a little tunnel there. The top of the ground actually will break in places because what was the surface is now having to cover more area, so there are breaks there. And the sedimentary rocks break, but the sedimentary rocks are not usually as strong as igneous rock, so they weather away more quickly. We'll talk about that in the next chapter, but they leave the more resistant granite peaks. And that's usually what you see in the Appalachians, okay? You may see some jagged peaks, but that's where the sedimentary rocks have weathered away and leaving the exposed granite peaks, which are a lot more resistant to weathering and erosion than the others. This is sort of the picture of it. Now, this happens extraordinarily slowly. It doesn't happen in anyone's lifetime. It just happens gradually over time. And we'll talk about the end of this chapter, some of the processes that do this that are creating the folding. This would be a dome mountain. Now, frankly, and I don't know if this fits the criterion well, but when I think of dome mountains, I think of, and it's not really a mountain, but it is an abrupt increase, but it's not that big of an increase around the surrounding, Stone Mountain in Georgia. Now, I think I asked the question before, and none of you had ever seen it, right? Okay, have you seen Stone Mountain? Oh, you haven't, okay. Say again? It's east of Atlanta, okay.
I might have seen it, I'm not sure.
What's that?
I might have seen it, I'm not sure.
Okay, yeah, it's, I can't think of the community. Smyrna, Georgia, maybe? I think that's where Stone Mountain is, but it's one of those communities east of Atlanta, east of Decatur, Georgia, you know. I think that had to be a dome mountain. I don't know that it was, but it seems like it had to be. Okay, but anyway, you get this, begin as a broad, arching fold, and the more it folds in the middle, the more the surface is stretched, and will start having cracks and crevices. Those allow erosion to occur, and you start losing your topsoil, losing the other thing. The sedimentary rock that's underneath, that gets weathered away, and finally the igneous rock underneath, it's the granite and stuff like this. It's a much harder rock. That's all that's left, okay? Not much of a mountain left unless that really has built up here. That's what I think happened with Stone Mountain. I don't know for sure, but my guess would be that. This is an illustration. I think in your book, oh, and by the way, I don't think they have the slide of this one. If you look at the figure 1917 in your text, and my book is around 491, they say there, the folded structure of the Appalachian Mountains revealed by the weathering and erosion is obvious in this Skylab photograph of the Virginia, Tennessee, Kentucky boundary area. The clouds are over the Blue Ridge Mountains, which are a pretty famous chain of mountains there. Mostly folded mountains. Okay? Then this illustration is, or someone like it, is on page 492. And let's see if they have the next figure. I think they should have, but they didn't. Okay? The figure 1918 is actually a shot of Sundance, Little Sundance Mountain in Wyoming. I've not been there, but I saw Butch Cassidy and Sundance getting out of that. Never mind. Showing the more resistant sedimentary layers that dip away from the center. Okay? That's the pieces out here. Oops. The pieces out here. Okay, this is sort of the surface that's eroded away. This is the upper part of the sedimentary part that is weathering away, but then some of this may be a little more resistant, so you have the ridges around the edges. They'll weather over time, but they're just a little more resistant than the next layer and the next layer. These are the most resistant here, generally. And you see that picture here too. All right. Now, fault block mountains, and most of the time when I'm thinking of these, I think Rockies, perhaps Sierra Nevadas, I think so, Himalayas, Andes. These are mostly faulted mountains, fault block mountains. They rise sharply along steeply inclined fault planes. Remember, your fault planes are either like this or like that, very steep and very distinct planes there. I'm not saying there's none in the Appalachians. There probably are some, but you see them more out there. Now, let me back up about the Appalachian things now. Which you reckon are the older mountains, Appalachians or Rockies?
One is on the Appalachians.
Okay, you're right on the Appalachians. You would think the Rockies would be older because they're so much taller. But guess what? The Appalachians are older because they're so much shorter. Why is that? Well, number one, the Appalachians have been around a whole lot longer. They're in the eastern U.S. where you typically get more rainfall. As we'll see in the next chapter, that's going to result in more erosion. Probably the Appalachians were some of the tallest mountains on Earth at one time, and now they're not much. That's the other reason they're sort of rounded, because erosion takes away the edges and rounds them off, okay? So that's the other reason. It's not just that they're folded mountains, that's part of it, but the other part is the erosion has rounded them up, okay? Now, are you skipping your tutoring today? All right. How about PE? Are you still going to go to that?
Definitely.
Huh?
I can't miss it.
Okay, I didn't think so. Okay. So, are you, what time is it?
3:30.
2:30?
3:30.
3:30. Is your second person usually in by then? Yes. Usually the second person's here for the lab, or she was last time anyway, wasn't she?
No, that was the count.
That was what? Oh, okay. Anyway, we'll see what goes on, but glad you're covering it now. Okay. Okay.
I just count this as work study.
What's that?
I just call it work study.
Okay. Okay, so the fault block mountains rise sharply. The weathering does erode the sharp edges away. So the older fault block mountains will be a little more rounded. The newer ones will be really jagged. That's how you can tell the Rockies are much newer. If you've ever seen the Rockies, they are pointed, jagged peaks. They're still growing, just like the Himalayas are. The Appalachians are actually, every time there's a rainfall and stuff, a little more is washed off. So they're actually shrinking in size, like old people. Never mind, we won't go there. Not that funny. Okay. Now, what would you say this is representing? Folding or faulting? The upper figure here. Folded or faulted? Faulted! You can see the fault planes here. Okay? Now, what kind of, let's start over here. What kind of a wall is this? Hanging or foot? Hanging. Foot on both sides. Hanging. Foot, hanging. Because the one underneath the curve, that's the foot wall. The one on the upper part of the slope, that's the hanging wall. What kind of forces would have created that fault? Three choices. Compressional, tensional, or shear.
I'd say rational.
Okay? Not. Okay? It's tensional. And here's why. Notice the tension's this way and the hanging walls are sliding down the foot wall. That means if they were compressional, they would be forced up the foot walls. And Carl is here. Okay. I want to call you Paul Sagan, but you're Paul Sagan. All right. By the way, anyone who came in after the very first, I did return your test 3 to everybody that was in here. So during lab or a test today, see me and I'll give you your test 3. Okay. And by the way, I guess, maybe that's where Carl was. Did you go to the locker room thing? No, okay, I didn't think so. But anyway, they had that today at 1. Oh, and here. Here it is. What's that? Okay, and again, I did return test 3 to everybody who was here earlier, so this afternoon when we're doing, this afternoon when we're doing either the lab or the test, if you'll see me about your test 3. Did you get that? No, you didn't. Earth to Darius, come in, please. Never mind. I returned test 3 earlier today. So during the lab or the test, see me and I'll give it to you. Okay. All right. So this is, tell me again, vaulted mountains. What kind of forces? Or stresses? Tensional. Okay. Now I don't know if you remember this. These were called Gravens, and that was called a Horst. Is that right? Get it back. I think this was the Graven, and that was a Horst. Okay. Doesn't matter on that, but just names that you like. Now that's what they looked like when the fault first happened. When there was a sliding down, and it wasn't immediate. It was gradual over time, but shortly, while it was happening, it was pretty distinct. Over time, though, weathering happens worse at the corners, because you have more surface there, and it wears off, and some of the weathering fills in the Gravens and wears down on the Horsts, and soon they sort of equilibrate a little bit. Now, if this turned into rock here, what kind of rock would this be? What kind of rock would that be if that turned into rock later? Sedimentary, because it wore off what was there, which could have been sedimentary, it could have been igneous, it could have been metamorphic, whatever it was, it broke down, filled into the valleys, and then piled up, and if it formed rock again, that would have been sedimentary rock. Okay, good deal. Now we move to the third type of mountains, volcanic mountains. A volcano is a hill or a mountain formed by extrusions, that stuff that's come out of the earth, of lava. Once it's out, it's lava. What was it before it was? Magma. Or rock fragments from the magma below. So some of that coming up could have carried rock with it that didn't quite get melted all the way and carried it along. So those rock fragments could be there. Now the structure they talk about here, and I think do a pretty poor job in the book and a really poor job on the slides of illustrating these. They have a great picture here, and guess who that is? It's a volcanic mountain. You can almost tell by, you can see the magma lava flows going down here. Which one's that? Probably didn't happen during your lifetime, but shortly before your lifetime. 1980, any of you alive then? You were? No, I didn't think so. Okay. Yeah, I was though. Okay. Never mind. 1980, Mount St. Helens lost her top. Okay. What happened? It had been dormant for centuries, and then all of a sudden erupted and blew the side of the mountain off. So that's where rock fragments came from. They blew off. Also, the crater was filled with previously melted lava, okay? So it was there. It blew out, and then all the lava flows later, and you can see where they were. I mean, you can see that lava flowed down and hardened in place, okay? So that's Mount St. Helens. Still spewing out steam, which means you're still pretty close to the surface, magma somewhere under there, heating that up, and steam is still making its way out. Meaning, it could have another explosion. But actually, did Mount St. Helens grow during that eruption?
No, true.
It actually reduced in size because the original crater was a little bit higher. It blew it all off, and most that came out filled in around here. It didn't build up that much. So actually, most of the time, volcanic eruptions create a growing of the mountain. In this case, it blew off such a big chunk off the top that it actually got smaller and shorter in size. Bigger around, but shorter in size. Now, what they don't show here is this structure, the vent, the crater, and the lava flow. Here's the crater, okay? Here's the lava flow. So those two are type, but they're not illustrated here. The vent is actually wherever the lava came from, okay? It could have been a little fissure or a crack. That's the crater that was left, but somewhere in there was the vent. And sometimes the vents occur on the side too. These are just clouds, don't get those confused. But there could be places where the vent actually comes out on the side rather than on the top. And there's nothing here that would indicate a separate top. But some of the pictures you'll see in your book, maybe not on the slides, will show places that they actually have, they actually look like two craters. One was probably a vent that came either before or after the other one. Okay. Now, as I said, the slide set doesn't show anything about the structure. This is a terrible thing to lean against because there's nothing behind it. It's a flexible screen. But if you look at this, I don't know how I can get up. Yeah, that's not bad. Right here. Basically, these are feeders, and wherever it comes to the surface, that would be the vent, I think. They don't do a good job of explaining here, a terrible job here, but that would be the structure. And you see this can sometimes be more than one place as they find their way up. You think of it being always at the top, but quite often it's not. Okay. So, that's just a brief introduction on volcanic mountains. There are three types of volcanic mountains. Okay? I don't know if you've heard any of these terms before. But basically, your shield volcano is, let me phrase it this way. They're more mounds than they're mountains. Okay? I don't know if that makes any sense to you or not. But they're constructed of solidified lava flows, and most of these flows have moved horizontally, not so much vertically, okay? It hasn't been building up much of a height at all. So it produces broad, gently sloping cones. They do have cones, but they're not cinder cone volcanoes. They're very gentle, very gradual. Now, if any of you have seen the pictures of the flows in Hawaii, I'm sure there's some big mountains in Hawaii, volcanic mountains in Hawaii. There's got to be, especially on the Big Island. But most of the volcanoes there that I've seen pictures of, and let's see if they got one here. I think they do. Yeah, here is one. Is this Haleakala or Mauna Loa? This is Mauna Loa. Okay? Oh, and here's the thing I was looking at before. Okay? This would be a shield volcano. Okay? Notice how it's not one huge mountain. It is a mountain. It comes up significantly off the surface. But it's solidified lava flows that mostly go horizontal and just gradually make these broad, gently sloping curves, cones on top. And this is Mauna Loa, and look at that. Mauna Loa is on, I think it's the Big Island in Hawaii. And you can tell there's several vents here, or places where they come out. One was here, one here, one here, one bigger one there, a little one there. Several places where it's found a crevice. Now, especially, and if you think of this, and here is Brittany. Okay. All right. A lot of the volcanic activity in Hawaii is on these. As I mentioned before, the ammunition ship I was on in the Navy was the Kilauea, which is the most active volcano in the world and has been for decades. It just always is spewing, but just gradual, very much a shield volcano. Always spewing out small amounts of lava, but not ever any major big eruption. Just always spewing. Okay. The second of these, which we don't have a picture of, is the cinder cone volcano. Okay? And what this is, it's steeper than the shield volcanoes, but usually smaller. So it goes up steeper, but smaller. The shield volcanoes can cover huge areas. In fact, I'm guessing several of the Hawaiian islands are just the remains of shield volcanoes. Okay? But these are steeper, but smaller than the shield volcanoes. Constructed of rock fragments, cinders that have been spewed out when they, like the top of Mount St. Helens, broke off, okay, and fell down. So those were the cinders, the rock fragments. The magma came up later, okay? I mean, came up, that's what blew the others off. But a lot of that was rock fragments. Now the big ones. The amazing ones, the ones that you always see the pictures of, are the composite volcanoes. Alternating layers of cinders, like you saw from Mount St. Helens, and it would be one of these, ash and lava flows with volcanic mud, okay? Because a lot of times these extinct volcanoes, the craters will form these beautiful lakes because, you've sealed off the bottom. They haven't been active for years. They catch the water. Snowfall melts. It fills them. Beautiful lakes. If you ever get up to Oregon, now I haven't seen it, but my nephew did, there is a lake called Crater Lake, and it's one of the more beautiful drives in that area. And there's a lot of beautiful things in the area. Have you been there? Yeah, that's on my bucket list too, I think. Yeah. Someplace I really want to go, Crater Lake, in places like that. So quite often that will be the case. So if you imagine when these things erupt underneath a lake, then there's a lot of ash that mixes with the water and forms volcanic mud. I don't know what kind of mineralogy that is or rocks are formed for that, but it's an interesting combination. Okay? So that's what these composite volcanoes are, alternating layers of cinders, ash, lava flows with the volcanic mud in there, and it's a mess. I'm pretty sure this is Shasta, isn't it? Have y'all got that one? That's one of the big volcanoes in, yeah, I think this is Shasta. Okay, boy, there's several really nice pictures in the book that are not on the slides here. I don't even see for certain, but I'm guessing this is the crater. It's really uneven. It's not just a perfect one like the others. That's probably the crater. Here was probably a vent that came up here. This was the picture I was thinking of earlier. Probably there was another that came off the side here, and that's what formed this sort of little smaller peak over here, and maybe some in there. But that's probably the main. Looks like there could have maybe been another vent or two here. But this is Shasta, okay? Big, magnificent, beautiful volcano, northern California. What's the one off Seattle? Anyone know? Mount Rainier. If you ever have a clear enough day, you're in Seattle or in the area or flying in or something, hope for clear weather. Not likely to get it, but you can. If you see Mount Rainier, beautiful, beautiful sight. Mount Fujiyama off Tokyo, another very, very spectacular volcanic mountain. These are your composite volcanoes. Notice here, I don't know if they show enough, these are lava flows. I can't read that. I'm going to have to look at the one in the book. The more recent lava flows and deposits are nearer the top, of course, the crater at the very top. other vents coming out on the sides, some buried still, older lava flows near the bottom. Okay, so that's basically what's going on here. Okay, this looks like a big lava flow. That must have been a major eruption. Well, that looks like a long way away. So maybe there was another one over here somewhere. I can't tell. The picture's not clear enough. But that's your major 3 types of volcanic mountains. Other features. Now, what they're talking about here, things not as big as mountains, but other things that come as a result of magma. Okay? Coming up, maybe near the surface, maybe on the surface. And Terry's here. All right, folks, we're down to missing Kanisha, Carrie. Carrie's been out for a while. Does anyone hear from her? Know her? What's that? She usually sits right over there. Sort of blondish, reddish. Okay. I don't know. She was very good attending early in the term and then suddenly dropped off the map. Brianna's not here yet. Don't tell me I marked you in the wrong. Oh, I forgot to mark. New Tire was here, but I hadn't marked you. You came in.
Mr. Fowler.
Okay.
Mr. Fowler.
Carrie and Keisha. So 3 of our.
I have a question.
Yes.
Do we have a certain number of absences before we fail the class?
That's hard to answer. I don't grade based on your attendance. I grade based on performance.
Okay.
So if you miss enough classes that you are going to perform really, really badly, yeah, you probably would. But I don't say, no, this many and you fail. No, that we don't. In fact, the whole college is not supposed to do that. We're not supposed to be grading based on attendance.
I have friends in other colleges, and they're
Yeah.
like, if I miss 5, I'll fail the class.
Yeah, and we used to do that when we were Western State Technical College, but even then, we were directed not to do that anymore. So I don't know, maybe they have different administrations. I don't know, but yeah, we're.
I've always wondered that.
Yeah, but basically, if you get the material, you get the material, and you get graded on what you get. Okay, that's how I do it anyway. Okay, I think most of the instructors here do. Though I guess, okay, I know some instructors count absences and tardies as non-participation grades. So if they have, say, a 10% or 15% participation grade, and someone's been absent a lot, they're not going to get those 10 to 15 points, where someone who's there every day will get all those points. So it might have some influence that way. I don't do that either. Okay, so let's look at some other features. Okay, this is a strange statement, the first bullet. What's strange about that? I would contend
All magma.
that all magma stays underground, because once it reaches the surface, guess what?
Well, lava.
It's lava. Yeah, so it's no longer magma. So all magma, but here's what it's focusing on. This is why this would not be a good test question. What it's talking about is remains underground. In other words, it never makes it to the surface. Okay? Most magma remains underground and cools in place. Okay? It cools and solidifies to form intrusive rocks, whereas the surrounding rocks may be sedimentary or something else, metamorphic or something, but the magma is suddenly a bunch of intrusive igneous rock right in the middle of other rock. Okay, we'll see a picture in a minute. Well, let's go on and show the picture. Okay, now this is showing lots of features all at once. Okay? What the red is down here was at one time magma. Okay? What the layers are would be what?
Sedimentary.
Sedimentary. Okay? Now what has happened here? Some of the magma, and we'll start with the batholiths here. Lith, meaning rock, okay? The batholith, these are rocks that have taken bath. No, not that. Okay, this has made its way to the surface. So this has made its way, or at least it made its way up there, and maybe the surface eroded away. We don't know for sure. But anyway, the batholith may have made its way to the surface, the magma to the surface, and then become lava. Maybe. That could have happened there. Here, it tried to do that and got significant progress, but never made its way to the surface. That would then form a stop. So the batholith was a large, wide area that probably did large amount of crystallized magma, whereas a stock is a smaller protrusion from a batholith. Okay? Batholith is big, the stock would be a smaller protrusion from the batholith. Okay. Now, these batholiths can cause hogbacks. Okay? Strange names. What's happened here, sedimentary rock usually sediments out horizontally, right? Until there is an intrusion or some sort of folding or something going on that bends them up. And that's why I say drive from here to Huntsville on I-65 going north and look at all the different road cuts and all the angles that you'll see the rock at. Sedimentary rock at all sorts of angles, you know there's either been folding, faulting, or intrusions of magma. Probably not so much intrusion of magma there, but if there had been, then you have this jagged area here where these sedimentary rocks that were like this have now been bent upwards, and worn away there. That was your hogback. Several different types of sedimentary rock, but on the edges kind of. Okay? Now, other of these processes. A small intrusion. Now, this magma, remember, is a liquid, has found little bitty creases. Here it found a wide area in the batholith or the stock, but here you found a little crease that it forced its way up. That's called a dike. Okay? They're almost vertical, close to vertical, and they go up. Okay? Those are the dikes. If they make their way to the surface, they could look like this. And this would usually be not just a single spout, but, two-dimensional. Okay? That would be evidence of a dike. Okay? Now, in the process, it may find a weakness in between these layers because the sedimentary rock came in layers, so there's usually an interface between the layers. And if in that interface the rock is not as strong or well crystallized or something, then the magma may make its way there. Those horizontal or nearly horizontal things are called sills. The dikes are nearly vertical, the sills are more horizontal. Now, say that one of these dikes over here made its way up and then hit a weak layer of sedimentary rock and forced it up, maybe like this or that, but the sedimentary rock hung on at least for a while. That would then be called a litholith. Okay, the batholith actually looks like the intrusive igneous rock made its way all the way to the surface. Here, it almost made its way, but there's still some, it was fed by a much weaker base than you had here, so it just made a mound here. And this would have been your dome mountain that we talked about earlier. And this is what my guess is Stone Mountain came as. It was just one of these things, and then the sedimentary rock eroded away, and you're left then with just the granite outcropping there. That's a litholith. So these are other features. They don't measure up to being mountains, but they do give you variations in either your surface topology or the subsurface topology, you might say. What's going on, or topography, I guess you would say, down there. So, it could easily be, if you're drilling through this or taking a core sample at sedimentary rock, and then suddenly hit some igneous rock and then more sedimentary rock, you probably just went through a sill. Okay? So those are the types of features that you can see from magma, but magma that generally didn't make its way to the surface. Almost to its surface here, pretty close to the surface here, maybe made its way to the surface there and there, but generally most of it did stay underneath. Any questions? We are that close to finishing, okay? But I think we're well, I don't think there's any chance that we're going, I'll say this and then regret it later, but I think we're going to probably finish plenty on time. So I'm not in any huge rush to continue, especially since this test is going to be a take-home anyway. So, well worth a read. Volcanoes change the world. That's not really an understatement. Okay, they only affect the area right near the volcano, you say, okay? No, that's not quite true. And read through this. There have been many volcanoes that spewed enough ash and debris into the air that literally it changed the climate for huge land areas because of the dust, the debris that stayed in the air. And read this, it'll tell you, for maybe a decade or more, dropping the temperature because the sun radiation couldn't get through to the earth, okay? And it dropped the temperature. And I think what they called a mini ice age or something like that. It just made it really, really cold for a few years. And it was mostly because a volcano halfway around the world erupted and the ash got into the stratosphere and stayed there for a long period of time. Well worth a read. One of my students several years ago, when she read this, she recognized Mount Pinatubo. She was from the Philippines, and she had seen that mountain just about all of her life, and she didn't realize what an impact it had had. She wrote her paper on the eruption of Mount Pinatubo because it was really important to her. There are several mentioned here. You might see something you would like to write a paper on. Okay? Let's see where we leave off. Overall picture. Where in the world is this? There we are. Man, we're in within a paragraph of finishing the chapter. Okay? But I'm not going to sweat it. We can finish it next time. And once we finish it, I'll give you your take-home test next time. And we'll do the lab then on the last 2 hours of that next class. All right, any questions? We didn't quite finish chapter 19, but we came awfully close. I think there's just like 1 or 2 more slides, and that's it. And it's time for us to start the lab. So what I'll do is turn off the projection, because I don't think we'll need it. Save on the bulb a little bit. And I may pause this ever so slightly. All right, we're back. We're ready to start the lab, so we're through with the slide set for today. I'll take care of that later. Yeah, there's the lab if you'll help him do it. Okay, I've given everybody a copy of the lab. Now, he may want to read it to begin with. We're not going to be filling things out yet. But if you will read the first part. Now, the materials, we don't have soft clay. We don't have a protractor and toothpicks and knife and pencil. Probably wouldn't be able to have a knife anyway. But the general thing is, take a look at the pictures here. Read this, and it's telling you what to do here. And it's the same figure you saw in the text. Let me make sure, yeah, I am recording. Same figures you saw in the text, and this is how you picture how you determine latitude. Imagine having a perfect sphere of clay, slicing it halfway along the equator and halfway down the pole, okay? So you get a wedge like this. Imagine setting up a protractor in that wedge there, that's measuring your latitude. That's degrees north or south if you flipped it over of the equator. And that's the figure 44.2. So we're not going to actually do that. You can picture this, read about it, and see what we're doing, okay, or what they're suggesting. Okay, then you put it on the horizontal piece that you cut out along the equator, lay it along there, and you see that you're going 0 to 180, and then you're going around the equator, and that's from the prime meridian here to the international date line over on the opposite side. And that gives you your longitude. So your latitude is measured north and south of the equator, 0 to 90 in each direction. The longitude is measured east and west, 180 degrees east or west from the prime meridian. So the pictures, I think, say it all. Now, based on what you've read in the first, 3 pages or so, is that my phone ringing or some other?
That's what I went down there and checked. I guess it's upstairs.
Oh, okay.
Unless it just stopped ringing when I got down.
Right. Okay, so that's 3 pages. No, 4 pages. 1, 2, 3, 4 pages. Read through that, and then and you can go and check in your book to use your text too. Answer the question, what information does the latitude of a location tell you? You can work together. This is a lab. You can work in groups, individually, pairs, the whole group of you, whatever. But answer those first 2 questions. What information does the latitude of a location tell you? What information does the longitude of a location tell you? Now, once you got that done, and you could be working on that, I brought up here an Alabama Atlas and Gazetteer, whatever that stands for. And what you'll do is take this, and especially if you've got someone who lives fairly close to you, and it almost opens right to the center. Almost, that's where it's always been. This shows Birmingham, Bessemer, Vestavia, Hoover, Centerpoint, Tarrant, Decina, Pleasant Grove, Hueytown, Dolomite. As far as Quinton, Jasper, a little bit of Jasper in it. Wattsville is just off Hell City, Leeds, Alabaster down here. Variety of places. I'm guessing most of you live on one of those 2 pages. If not, you can advance this way and get things to the east of us, Talladega, Anniston, that kind of stuff. Go this way and you get things out in the middle of nowhere, but here's Carrollton, Gordo, Northport, Fayette, Vernon, and Jasper. So it's picking up, not quite Tuscaloosa yet, okay? And if you want any other place in the state of Alabama, turn to the back and you'll see, well, I was just looking at number 30 and 31. The center of the page is right through the middle there. And when I flipped over, I got these 2. Flipping this way, you got these 2. And, you can go north-south, find the number, and then find that number in here, okay? There's 16 and 17, 24 and 25. The page numbers are the numbers here. So if you're not in those middle 2 pages, find where you live and find your latitude and longitude. Now, if you need help doing that, I will help you. And you should be able to get this to the nearest degree, minute, seconds, down to 0.5 seconds. So that gets it pretty precise, okay? So from this, you should be able to get that, okay? So once you've answered the first 2 questions, then y'all can start passing this around, working together, and find out the latitude and longitude of where you live, okay? Now, once you've done that, then explain how minutes and seconds are used to identify a location more precisely. Hopefully you would have seen that here, and just describe that. Now, you may wait to do question 5 until later, or you can do it now. But then over on the back of the page, okay, that's just 5 questions. Ooh, this is like the last lab. By the way, most of you worked on the last lab, and you got your questions done? Good. They'll probably help you on the test that you're going to do later today. Okay? So what are we going to do for the other 20 points here? Well, what I did was I brought with me 8 cups. Okay? And these cups have labels on them. Okay? The first of these cups is the Africa cup. The second one is the Alabama cup. Okay? The third is the Asia cup. The fourth is the Australia cup. The fifth is the Canada cup. The next one's the Europe cup, the South America cup, and then finally the US cup. Okay? Now, you need 10 more locations. Okay? In the cup, you will find strips of paper, barely legible. This one that I pulled from the Europe cup says Bucharest, Romania. Okay? Happens to be the capital of Romania. What you'll do, I've also brought in here, or actually Carl brought in for me, 3 atlases. Okay? If you choose the Africa Cup, the Asia Cup, the Australia Cup, the Canada Cup, the Europe Cup, or the South American Cup, then you'll need to get one of these 3 atlases. They all cover the same type thing. Find the country, find the city, and here again, work together in groups if you want to, and find the latitude and longitude of that. So we need 10 cities, right, for 10 latitudes, 10 longitudes. That's going to be your other 20 points. And what I want you to do, we got 8 cups, so that's going to be 1 from each cup, but you need 2 more. So you can pick a second one from Africa, Asia, or Europe. One of those 3, you can pick, in fact, 2 of those 3, pick a second city. Okay? So pick 1 from each cup, and either from Asia, Africa, or Europe, pick a second city. In fact, 2 of those 3, pick a second city. So you'll have a total of 10 strips of paper, right? If you want to do it on line paper, you can, or if you want to do it on this paper. List your 10 cities down this way, and then latitude, longitude. Okay? You'll need to use those atlases for that. Now for the Alabama Cup, you'll use this one. You'll pick some city out of the Alabama Cup, and it won't be on those 2 pages here because I picked them from different areas. Okay? So you'll pick 1 from Alabama, use this for the Alabama. You'll get very good precision on that. Okay? So you actually have 2 towns from Alabama, your hometown, plus the one that you draw from the cup. For the US Cup, that's this one, you'll use the Rand McNally thing. And if you have trouble finding latitude and longitude on there, I'll help you. I'll help you on any of these. Okay? So just ask. So the US Cup, you use this one. Any of the other continents, you use those 3. The Alabama Cup, you use that. Okay? I'll spread these around. I'll put this one right here. Now, don't hog an atlas. Get what you need and put it back. Okay? Get with a friend maybe or whatever. Any questions on that? And then once you finished it, be sure you answer question 5. 25 points, 10 cities, 1 from each cup, 2 from one of the 3 cups, Africa, Asia, or Europe. 2 out of the 3 get an extra city. Write those on the back. Put the things back in the right cups, by the way. Okay, don't put Asia back in the Europe cup. You know, that's not going to be nice to the next class. Okay, and then write your latitude and longitude. Any questions? If you have questions, feel free to ask. Yeah.
I'm just waiting.
What's that?
I was just waiting for you to finish.
Oh.
And the answer.
To do what?
You gave me the answer.
Oh, actually, okay.
Yeah.
Okay. So, knock yourself out. Start answering your questions. Start pulling. There's the Alabama over here, US there, and 3 world atlas.
North, south position.
What's that? Need one? Oh, we need a lab. Anyone else need a lab? Anyone not get a lab? Everybody got a lab?
North, south position for the extra 20 points is what we're doing. We're doing 10 cities.
If we finish early, can we start the test?
I'm sorry?
If we finish early, can we start the test?
Yes, if you turn in your lab early, you can start the test.
So, let's pick each. We have to pick 2.
2 from either
Asia, Europe.
2 of the 3,
Yeah.
Africa, Asia, or Europe.
Right.
I hope all that got recorded here.
I got Asia.
We need 2.
Okay.
Hey, did you get one for Canada? No. Go with Brad.
Oh, it's a maybe 2 of 1.
What's that?
2 of 1.
2 from which?
I'm gonna get one little one.
Huh?
I get
Okay, you get 1 from each cup and 2 from 2 of the 3, Asia, Africa, or Europe.
I got it.
But put them back. Don't hang on to them. They're not yours for keeps. They're not souvenirs.
Sorry, can we get
Write them down and bring them back and put them back in the cup. So you can share with your friends.
From each cup? No, like, you only supposed to get 2 from Asia, and the rest you just get 1. So, if you want, so if we each take a
Okay.
city,
If you get 2 from Asia and or 2 from Africa and 2 from Europe, just do 2 with 2 and 1 from all the others. But make sure the 2 come from either Africa, Asia, or Europe. And I got plenty of labs,
yes,
don't I? The lady in the copy room ran the labs twice, so we got 15 of them. Why we do not do it.
I'm sorry, they need 2 of 1.
2 out of either Asia, Africa, or Europe. Wherever Europe is now, people are hauling things around. I'm not sure they're in the right order anymore. I'm sorry? Latitude and longitude of that city. If you have questions, ask. I'll be glad to try to answer.
All the cities are the
Huh?
all the all the ones you pick.
Okay, yeah, you pick 10 cities
Okay.
and then do a latitude and longitude from each of the 10 cities you pick. And don't hang on to them forever, bring them back and put them in the right cups.
Yep.
When 3 o'clock gets here, I'll call again. I gotta leave by 3:30.
Well, yeah, I still gotta
I was
go.
gonna say it's probably.
Oh, you do, okay. Whatever you need to do. We'll get someone else that. Have that.
What decimal point?
What's that?
What decimal?
Oh, wow, Atlas.
Which are you doing?
Latitude,
Okay, but, what city are you talking about?
Jerusalem.
Jerusalem, okay. Are you finding an atlas or are you getting it on the phone or computer? Okay, yeah. Whatever they give you, you can do it to that precision. Yeah, because you see in the atlas, you may not even get better than a degree.
I'm saying like.
And others, you might be able to get degrees in minutes. Alabama, you'll get degrees, minutes, and seconds. So if you're using a phone, you get degrees, minutes, and seconds. Yes. You can't find what? I can't hear you. Panama? Panama City, I think. Oh, this is Panama. Okay, this is not Panama City, Florida. This is the country Panama. You will need to use an atlas. This is a different country. This is only U.S. Okay.
Well, that's kind of that's socially made for the skeleton.
Well, then they had it wrong. See, some people didn't put it back where it belongs. Oh, yeah, this is Panama City, Panama. Okay. Now, what you need to do is
Almost done. It's done.
I just had that song go up in my head right before you said that.
Look, you can't just say that and like not think.
Yeah, really kept you tuned.
Where does this sound?
See it? Yeah, they don't say it. See, this is the country from here to here.
That's the capital yeah, that's it.
Latitude is which one? Latitude is north or south of the equator. Okay? Now,
Oh, yes. Your route. Okay, more
Let me go put this back.
That would help.
And I found
Four.
the answer to the second.
Actually, give me a
six, eight, north of the equator. By the way, folks, before you're writing too much, when you write a latitude, you better have not just numbers, but north or south, N or S, because you got to be north or south of the equator. Unless you're right on the equator, then 0 will do. If you're writing me a longitude, you got to have the letter either E or W for east or west, whether you're east or west of the prime meridian. Okay. Yeah.
So,
Okay, I'll put
Get
you.
your assignments in here.
Okay,
So
where are
that
you?
is
All done.
where?
Yeah.
Grade
Musicians?
Okay. And as far as latitude and longitude, how would you find that?
I guess this line is
176 what? Really? And this is the first part of your lab.
I know, yeah.
Okay, what does that? What does latitude tell you? And you want to have a clue? That's one of the important, get those first questions right. What does latitude tell you?
Latitude tells you the distance from the equator to.
From the equator,
I got
north or
this
south of
10
the
written
equator.
down.
This is telling you something east or west of
I'm
something.
gonna go
So
ahead
this
and
is your
fix
latitude
that.
up here.
I'll let Eric help me.
So, where are you?
He can
The latitude line.
Dr. Fowler, I'm
Can you
confused.
pick something close?
Me too.
Yeah. Okay.
I got these 10 cities written down in these first 2 questions. He's already in. I never forgot that.
Okay, good.
Just the coordinates.
Okay. Go lift. Okay.
Get live.
Yes.
This is recording.
Okay, yeah.
Well,
Yeah, okay, yeah. This is the latitude. Latitude south.
Longitude east west.
Latitude south.
but I'm glad you just
Okay. Okay. Since it has for degrees in English, I would use this one. Yeah. I mean, you see, that's the minus means south, and that's the decimal number. This would be the latitude. I mean, that's the latitude. This is the longitude. So I would use. If you have a choice, do degrees, minutes, second. If your source only has fractions of a degree, then it's okay to use that. But you need to use the symbol. Brittany, could I ask you to work with him on this? Okay. And you can do them too. Just write them down for both of them. I know you probably already got.
Yeah, I know, like, I don't know where it is.
So if you just do. I'll put that down for worksheet.
Well, I'm talking like of the
Other people did. Will use them too.
second.
Huh? Yeah. Okay.
I guess
I'm
I'm
guessing 0 would be.
I put them there in the first place.
Okay.
Tasmania would be Australia.
Yeah, you said
South.
you used to do the or you use
Philippines would be Asia. And Congo is Africa. Okay. All right, did I answer all the questions? I got interrupted a few times.
Correct.
Yeah.
Latitude is north and south.
Yes, that's,
Okay.
yeah.
Yes.
All I'm doing is
That's the one.
going on here.
How do you know if it's east or west?
That works for me.
Okay, cool.
Saves me better on accountants, and saves me better on which is
Yeah.
East or west?
How did you come to be
It's good. So I actually got one of the ones you got, and the other ones, since you already got them, I'll just stop with them.
So you must
Unless you wanna use this one.
Yeah.
79 degrees west. Yeah. And zero. That's west.
Huh.
That's
4 degrees
That wasn't, hey, remember, that wasn't US. That's where it was, but that was South America is where it should
We
be.
turned out
Brittany, you can do his instead of yours, you know, that's what I'm saying. You don't have to do two different sets.
what is it?
Let me make sure that's in the US, is it? Yes, that's the US, okay. Good. All right, it is after 3, so I'm going, if I can find my pen, I'm going to mark roll again. Brendan is kind of still here, okay? Brianna didn't make it in today. Darius is still here. Emmanuel is still here. Tara, oh, I saw you earlier. Oh, there you are. There you are, okay. I knew I'd seen you would talk, okay? Coco is still here.
32 degrees.
Bianca is still here, I see you.
83 degrees.
James is still here. No, James is in Puerto Rico. He was in Auckland, New Zealand. That's where he was. Okay. Josh is still here. Down to yeah.
59.
Carrie didn't make it in today.
19.
Carl is still here. I think. Yeah, that's Carl back there. Kenesha hasn't made it in yet today.
What's the next one?
Shelby is still here.
5 degrees.
Brittany's still here. And Carrie's still here.
20.
Okay.
4, 9, 1, 7.
All right.
4. West.
Oh.
So we already have Congo.
What? The,
Sorry.
It's fine. Yeah.
And say so.
I don't mean to interrupt the lab, y'all keep working, but let me go through this again for people who weren't here before. I've received 5 papers in out of 15 students. That's not bad, but we need better. Lab 1, I still have 2 people who haven't turned in lab 1. 1 person that hasn't done test 1. Lab 2, 2 people haven't done lab 2. Test 2, 2 people haven't done test 2. Lab 3 was the moon lab. I'm still waiting for my, yeah.
I need the lab for Tuesday.
For Tuesday, you need the lab? Okay. Okay. Say it.
I have
The
like,
questions were the last question.
Okay. You'll need to listen to screencast or YouTube to get the information. Here it is.
here
to get the information, and then, as she was saying, you need to answer 15 or more questions from the end of chapter 18, from the 16 questions for Paul, and 4 questions for further analysis or something like that.
Do I have to do 16 and 4 or just 15?
No, any 15 of those 20. Okay, so I haven't gotten any moon labs in yet, but the good news, team, is that everybody, I'm not going all over the floor. Okay. 39.504. Okay, test 3. Brianna's not here yet, excuse me. Darius is. Bianca is. James is. Carrie's not. Carl is. Kanisha's not. Shelby is. Brittany is. And Carrie is.
50 feet.
What? Be sure you get your little slips of paper back to me. Don't walk out without them, with them. Yes. Okay. Yeah. I just did that. Okay. Which one you look on? Boston, Massachusetts. Okay, there you go. Okay. Now, this one isn't showing latitude, longitude. You'll have to go to the this one. Yeah, east. There's Boston. And
42 degrees.
the latitude is measured from the north-south, so that would be the numbers along to here. And longitude is east-west, those are numbers. Yeah, it's them right up here.
55.
Boston, you got latitude is here's the upper, and where's the lower? It'll be between that number. Here. Okay, so fixed on level ground. Longitude will be between, I don't know that number right there, maybe do it this one. Be sure you add east or west to longitude, north or south to latitude.
No, man.
Okay, that is, okay. I'm just kidding. Okay. You get one, too. Okay. What's that? Sorry.
I just got this number to you. I think you got
Okay, what are you looking at?
yes, ma'am. Someone, whoever
Ari?
her name was Jessica something.
I'm trying to find
Is that everyone's asking for Jessica? So
Okay.
that's the only thing.
No.
it's Barbara, what do you mean?
Okay, and just right near where your finger was.
Yes, ma'am.
Down,
Thank you.
down, 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 down. Right, 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 right.
Doesn't he have a phone number?
Oh, there you go.
There it is!
Hey, so hey,
I know, right? Terrible. Okay, what's the next one?
Okay. So the
How
next
far?
one is 147 degrees.
how far is from, Spotwood?
How far you are, north or south of the
90 what?
19.
equator?
19.
On the brother
That
south.
might be set.
Say again?
On the brother south.
You're about what?
South of the south.
Okay, wait. Okay.
And
Then
then it's 37.
You need to sort of find the equator. Okay.
Good.
Folks, if it will help you to sort of locate where you are,
it's
here's a globe.
19
Okay. Now, obviously, you're in Africa.
okay. 37.
And you're in Zimbabwe, which is down here. So what would you say you are relative to the equator? Here's the equator.
Now,
Here's Zimbabwe. Where are you? North, south, east, or west? Of the equator? Here's the equator.
Yes.
North is up, south is
You
You're
have
south of the
two
equator.
from there.
And right on here, you can find the equator right there. It's 0 degrees. That is the equator right there. There it says it.
Europe,
out
Asia,
there.
Africa.
Equator.
So we can't.
Oh, okay, so like this right here?
Yeah, so that line here
But
goes
I
right through
have
it.
two.
Read how many
Yeah, I'm
degrees you are
Yeah.
south of the equator.
Okay.
You put two up.
Okay.
I guess
Okay, and then east west would be
Or
this
it
way.
was just
Find the
something
number
Yeah.
at the top or down bottom of the line.
Okay.
What you doing now? Huh?
Okay.
Oh, I see. Okay, good. Okay. I think I returned all the papers to everybody who was here. And as I was continuing in lab 4, which was going to the planetarium, if you went, you got a 25. If you didn't, you don't. Okay?
Oh, I
Lab.
have a question about that too. When I went up there, I was lost, so I couldn't find it. But then I went the next day,
Mhm.
and I actually found it. But I thought it would be showing every day. So when I found it, nobody was in there. I was like, oh, okay. So I guess. So is there any other? Is there any other showtime that I can come and see?
Well, you can contact the planetarium. It's the Christenberry Planetarium in Sanford. You can find the number on the phone book or on your phone probably somewhere, and call and see if when he's got another show.
Okay.
It may be a different show from the one we saw, but it's still going to be good. I bet.
It was beautiful. It's big. And
Yeah.
I've never been in a place like that. We're Brisbane, Queen.
Yeah, that's Australia, right? Queensland, is that? Huh?
So it's Australia.
Yeah.
You know about
Oh, Brisbane, Queensland,
So
yeah.
it's not Brisbane.
Brisbane, yeah, either one.
Oh.
Can be pronounced. All right, look at her, she's gonna put them all back in the right boxes, okay.
So I'm going to
Yeah,
and so is Tunisia.
Tunisia is also very close.
And Croatia's your,
What is
What's that?
is Croatia?
Yeah.
7 degrees.
And it's is it Asia?
Nation.
And it's
Okay, continuing after lab 4, which is the trip to the planetarium. Lab 5, I still have two people haven't turned in lab 5. Test 4, 1, 2, 3, 4 people haven't done test 4, and we're currently working on lab 6.
153 degrees. 1 minute. 30.4464
seconds?
Yeah.
Whatever. I think they're in Southeast.
Just from the Israelis kind of the corner.
Yeah, it's true.
So if you already have
Can you see it?
Yeah, I can hear.
I think Liberia is in Africa. Yeah, that would be fine. You've already got the name? Okay. Which one's that?
40 degrees.
Well, no, Liberia is
0 minutes.
someone got them all. Have you already done an Africa?
two Asians
Okay.
and two
You get to do 2 if you choose.
Seconds.
Okay. So what about your?
23.
So we only have one?
42.0924.
Stop here.
We got.
All right. Excuse me.
It's 20 from the
Thank you.
Right there?
Okay. Anyone think there'll be any other questions? I'm thinking of pausing. I'll go on and pause integrity. I'm still talking integrity.